So, sorry, I'm a little bit sick. Uh, so second question is the MLE applied to the linear regression model. So the difference here is the full rank assumption is maintained, linearity assumption maintained. The difference is the exogeneity assumption is strengthened. So exogeneity is replaced by a stronger assumption of normal distribution. So epsilon conditional on x follows normal distribution. What it means is, so even if you are conditioning on x, the distribution does not depend on x. So no matter what x is, the distribution is always the same, which means epsilon is independent of x, right? So it implicitly implying that epsilon is independent of x. And I use gamma in here because sigma square can be confusing in notation. So I will use gamma instead of sigma squared. So gamma is the variance, and theta, the parameter, is a vector of beta and gamma. Then what we are interested in is the probability density for y conditional on x. X is an exogenous variable, so we are not interested in the distribution of x. We are only interested in the distribution of y conditional on x. And this is basically a normal distribution with mean equals to x beta 0 plus variance gamma. And some bound conditions. Actually, this bound condition is not it's not ideal. Later I will explain. So this is the problem when I make a question without answering that. So when I write down the answer, I find this part is not good. Okay, then normal distribution PDF is like this. So have a look at that. So I will do it one by one. So by the way, this is just my answer. I just try the homework as a kind of as if I'm a student answering that question. So my algebra may be wrong. I did not proofread my answer. So be careful. But the idea, I try to deliver the idea, not the algebra. So it's your responsibility to make the correct answer in your exam, even if you have the same question in the exam, and even if my answer is wrong. And the PDF takes this form. PDF of y given x is a normal distribution with mean, and variance gamma, right? By the way, beta and gamma is included in theta. So by taking the log on this PDF, you get log likelihood function, and straightforward log, take log, and then derivative with respect to theta is 2 by 1, not 2 by 1. So this is k by 1 vector, and this is 1 dimensional scalar. So totally k plus 1 vector. And for each of them, if you differentiate with respect to beta, you get this. With respect to gamma, you get this. So nothing to explain. It's straightforward calculus. And second derivative, also nothing much to explain, but just remember the form. So in here, it is k by 1 times, k plus 1 times k plus 1 matrix. So this is the first diagonal block. This is the k by k block, and it is k by 1, 1 by k. I had to transpose here. It's my bad. I forgot to transpose beta here. Here again, I had to transpose beta again here, so it's my notational problem. But assume that beta is scalar, still not a problem. So everywhere I made a mistake in the notation. If beta is a vector, I had to use beta transpose, d beta transpose. Anyhow, so match the dimension. Then you can also differentiate these guys to obtain them. obtain those things. Straightforward calculus. And now we will see the maximization of the criterion function. Criterion function is the expected value of, so we just answered this guy. And criterion function is the expected expectation of log likelihood. So this question is pretty much the same as what we did in question 1. So simple. First order condition, second order condition. Check the first and second order condition, and the same as before. I'm going to skip that. And Hessian matrix. So we need to check the Hessian matrix for here this question. Hessian matrix is the second derivative of the criterion function, and we need to show that it is non-singular. In this case, the Hessian matrix, this is 0, this is 0. So we call this kind of matrix as a block diagonal matrix. And block diagonal matrix is non-singular if each block is non-singular. And it is non-singular. This is non-singular, this is non-singular. So that means it is non-singular, obviously, from the full rank assumption. And this is non-singular as long as gamma is non-zero, right? So we can say that H is, the Hessian matrix is strictly negative definite. So the second order condition is satisfied. So that's nice, going well. And now then variance matrix. Variance matrix, also it's just tedious algebra. Variance goes like that. And especially now, by the way, variance is calculated when theta equals to theta 0. Theta 0, so it is at theta 0, so we have some epsilons. When y minus x beta 0 is epsilon, so then the formula is complicated but not much. Remember, then here it may be difficult. How can we proceed from here? You know how to handle this. But we have epsilon cubic squared and to the exponent of 4, and it follows from the normal distribution's properties. Normal distribution's third moment is 0, which is skewness. So skewness is the third moment. Skewness is 0. And kurtosis, the fourth moment, is given by 3 times variance squared. Even if you don't know them, it's fine. Just it's not important. It's just well-known properties, but not much important. But it would be nice if you know them. And then apply the law of iterated expectations, then everything will be simplified. So it will be cancelled out and cancelled out. It will be 0 and something cancelled out. So in the end, you get this. I think there is a typo. It must be 2, I think. Should be 2. Yeah, I think it's wrong. So check it. And then, so we just answered this and this. Now, part E is to calculate in the finite sample. In the finite sample, we replace the expectation with finite sample average. Sample average can be written in this way. Let me see. 1 over n. There must be 1 over n, but I forgot to write that down. There must be 1 over n here, but does not change the result. Then you can calculate. This is identical to the least squares first order condition. So this condition is equivalent to the least squares first order condition. So you get beta here, and using this beta and plug that into here, then you can obtain gamma, estimator for gamma. Then you get this. So so some student, like in the past, some students ask me what is a closed form solution. closed form solution means that we want to write the answer equals to something. So like if you solve for x, I want to say x equals to something, right? That is the closed form solution, right? So when for example, if you say that beta 0 is the minimizer of this is not a closed form solution. But if you say beta 0 equals to something, then equals to say, so for example, if you say beta 0 this way, if you have like this is a closed form solution. Of course, when you replace expectation with like finite dimension, a finite sample counterpart. So closed form solution is literally a formula for the solution. And then the cumbersome part is to show the boundedness. Just idea is simple. Just we need to bound everything. Assume everything is bounded. Then we have to prove that, like combining them together, our function is bounded. So it's like this. It's just expansion of the square, but everything is turned positive, like turned to absolute value, or square is automatically positive. It's positive, but this part is taken absolute value. It's true for any beta. And we apply Cauchy-Schwarz inequality on here. So we would like to bound x and bound beta separately. So we'd like to handle them separately. So we separate them using the Cauchy-Schwarz inequality. Cauchy-Schwarz, and then this inequality becomes this. So as I said, what we want is we will bound this, bound this, bound this, bound this, this. So everything, every single term is bounded. If you can assume them, then you are good. By the way, I found yesterday when I write the answer, the question was wrong. You have to erase this part. You cannot have this because when you took supremum of theta, the right hand side cannot have beta. So like supremum is uniform over beta. No matter what beta you have, this inequality has to be satisfied, but it is specific to a beta. So it's wrong. Something is wrong. Like my notation is wrong. Question is wrong. So what's wrong is you have to delete this guy. You have to delete this guy. So not a big problem. You know what we are doing. And then all the other guys, straightforward. Just annoying bounding. Again, the idea is you bounce things, and see what you have in the end. And maybe the standard way to show that something is bounded is to show that there exists a constant that bounds everything, bounds something. Like in this case, I define another constant, which is a maximum of two constants. So these are constants, so their maximum is also a constant, and it cannot be infinity because each of them is not infinity. And then we have C2 must be greater than 1, right? And you have this and this, and therefore we want to rewrite gamma this way. Bound gamma with from below and from above using only one constant. This will be more convenient when you take the log. Take log, then log of gamma is bounded from both sides by the same constant, log of the same constant. So we have this. So that this is why I wanted to have this. So so the notation in the question was not good because this is more convenient way to denote the bounds. And also we can bound 1 over gamma by C. So we can bound this. This is constant. Pi is 3.14. So this is just a number, constant. So you nothing to bound. You bounded it. Now this part was bounded above. So everything is bounded. So combine everything, then you get these things, and take expectation, you get these things. Apply the Cauchy-Schwarz inequality again, and then everything is nice. Everything. I forgot to do this. But should be easier. Like should be similar. Like second derivative. Where is the second derivative? Second derivatives are these guys. So you can bound this, straightforward. So try that. That will be a similar good exercise. And then combining all the results, you can just verify each of the conditions that I wrote down in the lecture note, and then calculate that. And then remember, I said this was wrong. Should be 2. So should be 2. I don't know. Something is wrong. I think something is wrong. I don't know where it is wrong, but yeah, I'm sorry. Sorry about that. It was wrong. So it seems like something is wrong. It cannot be this simple. So it is your job to find where it was the mistake. You understand? Okay. So thank you for watching. It was very algebraically cumbersome question, but this is maybe the easiest example we can think of in this estimation chapter. So as you learned from the class, the theory itself is very complicated, so this is not that bad. Okay, hope you enjoyed it, hope you understood this, and see you later.